Okay, what if our computers could understand the world, like a human brain does? Today, we're diving into this really fascinating AI called semantic folding. It's a technology that's all about teaching machines to grasp meaning, not just to process a bunch of data. Let's get into how it works. This is the big question, right? It's what's pushing AI to its absolute limits. We've built these incredible machines that can calculate and spot patterns at mind-bending speeds. But true understanding, getting the context and the real meaning behind words or signals, well, that's been the holy grail.
So, to really get why we need a new way of thinking, we've got to look at where AI is right now and one of its biggest challenges: the unbelievable amount of data it needs to function.
For a long time, the trend in AI has basically been go big or go home. More data, more powerful chips, bigger and bigger models. But honestly, this whole approach is starting to hit a wall. We're seeing diminishing returns, and the costs and energy use are just skyrocketing. So you have to ask, is just getting bigger and bigger really the only way forward?
Look, these traditional AI models are no doubt incredibly powerful, but they've got some serious downsides. They use a massive amount of energy. They can be surprisingly fragile when they run into something new, and their decision-making process is often a total black box. It's almost impossible to understand why they made a certain choice. It's becoming pretty clear we need something smarter, not just bigger. So where do we find a better way? Well, the solution doesn't come from building an even bigger supercomputer. It actually comes from studying the most efficient and, frankly, most powerful learning machine we know of, the human brain.
And this isn't just a small tweak we're talking about. It's a complete shift in how we think about the problem. We're moving away from just recognizing patterns in raw signals to actually understanding the semantic content, the real meaning of what those signals are trying to tell us. And that brings us to the main idea here, semantic folding. At its core, it's a method that takes any piece of information, could be a word, a whole sentence, or even raw data from a sensor, and it turns it into a unique semantic fingerprint. You can almost think of it as a universal translator for meaning itself. Okay, so how does this actually work, right? How do you create a fingerprint that literally captures meaning? Well, it all starts by building a map. The whole process kicks off by taking a massive amount of text, think all of Wikipedia, and creating what you can picture as this giant two-dimensional map of meaning. On this map, every possible topic has its own little spot, and similar topics are clustered close together. So the neighborhood for cars would be right next to trucks and transportation, but way, way across the map from something like baking recipes. Now, here's the cool part. To figure out the meaning of a specific word, let's use jaguar, the system finds every single time that word appears in all that text. It then puts a pin on our map for each of those different contexts. The result is this totally unique pattern of pins spread all over the map. And that pattern is the semantic fingerprint. It captures all the different meanings, the animal, the car, maybe even a sports team. And what's really amazing is that this whole process is completely unsupervised. No human has to teach it. First, you just feed it a huge reference text. Second, it chops that text up into little context-based snippets. Third, it arranges all those snippets on the 2D map, grouping similar ideas together. And finally, to get a word's unique fingerprint, it just plots every single context where that word shows up. And the result is so elegantly simple. Because of the way this map is built, if the fingerprint for car and the fingerprint for truck have a ton of overlapping pins, we know their meanings are super close. All of a sudden, we can compare meaning with math just by measuring how much two fingerprints overlap. It's that straightforward.
All right, now this is where the technology goes from just understanding language to understanding the physical world around us. And trust me, this is where it gets revolutionary.
So get this, the exact same method we just talked about for words can be applied to raw sensor data, a specific vibration pattern from an engine, a radar blip, an electrical signal. All of these can be converted into their own semantic fingerprint. The system literally learns to connect signal patterns with specific meanings, like everything's running normally versus, uh-oh, impending failure. And you can imagine the applications for this are just massive. Think about those high-stakes industries where understanding tons of sensor data in real time is absolutely critical. We're talking aviation, automotive, advanced manufacturing, and of course, defense. In aviation, for instance, semantic folding can analyze radar signals to not only classify what it's seeing, but also to spot weird anomalies in real time, which could drastically improve air traffic safety. It can learn the difference between a bird, a commercial drone, and something completely new and unexpected. And for self-driving cars, this is a game changer. It allows for way more accurate and reliable fusion of all the data coming in from cameras, LiDAR, and radar. This leads to safer, much more robust decision-making on the road, because the car isn't just seeing its environment, it's starting to understand it. Or how about in a factory? It can be used for predictive maintenance. By understanding the meaning of tiny vibrations in a piece of machinery, it can detect that a critical pump is about to fail long before a human ever could, preventing super expensive downtime and keeping people safe. Now, one of the most powerful things about this brain-inspired approach is just how incredibly efficient it is. And that efficiency means it can run almost anywhere. Because comparing two fingerprints is a really simple operation, this kind of AI doesn't need a giant power-hungry data center to work. It can run directly on small edge devices, the actual sensors in a car, on a drone, or on a factory floor, giving you real-time intelligence right where you need it most. So what are the big takeaways here? Well, semantic folding lets us do unsupervised anomaly detection. It can spot problems it's never even been trained on. It's super adaptable, it's not bothered by noisy or imperfect signals, and maybe most important of all, it's incredibly energy efficient right from the ground up. When you think about it, the future of AI might not be about who has the most raw power. It might just be about who can build the most elegantly efficient systems. Systems that are smarter, more adaptable, and way more sustainable. We have really just scratched the surface of what becomes possible when we stop just processing data and start truly understanding meaning. So it leaves you with this thought. What could a world full of genuinely intelligent devices actually look like? The possibilities are pretty staggering.